my favorite curves are parabolas. Let's find the area enclosed by two parabolas. Let's find the area enclosed between our favorite parent function parabola, y equals x squared, and my favorite stretched and moved parabola, 2x minus x squared. Not stretched, just moved to the, looks like it's moved to the left. We'll have to figure that out. I want to find the area between these curves. Now, I don't have to have a graph, but I love graphing. I live for it. So I'm going to graph the two functions. Y equals x squared. Whoop, whoop. All right, there it is. And then I'm going to graph, and I'm going to think of it this way. Do you guys agree it's this? And I might use the intercepts. You guys see, if I pull out a negative x, I get x minus 2. And we know parabolas are symmetrical. So I can plot 0 as an x-intercept, and I can plot 2 as an x-intercept, and I know the vertex is at 1. I also know this sucker opens down. You guys agree? Well, I can find that region. There it is, right? In all its glory, right here. You guys agree? And I can see where I can even see where it starts. Right? I can see it starts here at x equals 0. And I know what the curve is. I know the green one is the top curve, right? So I know it's this curve minus that curve, right? For y top, y bottom. But what's the one fact I'm missing at this point? Where am I going to end this integration? Right? Friday afternoon, not waiting for you guys. I don't think it's 2 because 2 is there. I got to figure out this intersection point, and I'm just going to call it B for right now. Guys, everybody, we should see from the graph that A is 0. All right. But I wouldn't need that because I could look at these two curves and say, hey, y equals y. So guess what? X squared equals 2x minus x squared. 2x squared minus 2x would equal 0 if I put everything onto the left, pull the 2 out, 2x out. All right. Where's my math mistake? Oh, it's not 2. There's my math mistake. Friday afternoon math mistakes. You guys are letting me make them. And what do we get? I get two answers here, right? X is 0 and x is 1. Guess what B is? B is 1. So now it's really easy. We know what curves top. We know that they intersect at 0 and 1. Let's do the integration from 0 to 1. The top curve is the green curve. 2x minus x squared. The bottom curve is x squared dx. And here's the great thing. I can do like terms before I do integration. So I'm going to combine like terms. And I'm going to say I'm going to integrate from 0 to 1 of 2x minus 2x squared dx. If I want, I can pull the constant out. All right. That's one of the rules we put in there. And now I can integrate x minus x squared. The antiderivative of x is x squared over 2. The antiderivative of x squared is x cubed over 3. Both of those things are evaluated from 0 to 1 with the 2 hanging out front. I don't have to have plus c because it's a definite integral. C minus c is 0. We're looking for an area. I take 2 times, how about 1/2 minus 1/3? And then I do it every time. 0 minus 0 if you plug in 0. Last time I checked, 1/2 minus 1/3, I'm going to get a common denominator 6. 3/6 minus 2/6 is a 6th. 6 times 2, when you do all the math, guys, the area between those curves is exactly a 1/3. And this is where we're going first part of next week. We will be just given curves, finding the where they intersect, the understanding that when curves intersect, you have places for the limits to occur. And then we will, once we get really good understanding with these x, we're going to rotate our world and do these integrations with respect to dy. All right. Don't give up. Keep practicing.